Hi, I'm Andy Davidson, founder of Financial Lifecycle Education Corp. We're a not-for-profit that works on connecting math to personal finance, and we're also known as FiCycle. Today, we're going to be talking about data science and credit scores. This is part 3 of a series. The theme of the series is, can we use data science and mathematics to answer the question, am I my credit score? A little bit more about FiCycle. FiCycle, as I mentioned, is a not-for-profit, and we're really focused on combining mathematics and finance in education. And we have various aspects to what we're doing. We engage in research. We've developed standards. We've developed a full course, use the 3rd or 4th year course in high schools. And then we have various modules and lessons to help teachers increase the use of mathematics and financial education materials together. As I mentioned, this is about credit scores, and we're developing a series of lessons around credit scores. If you're interested in these lessons or more information, please use this QR code to reach us and fill out the form. So as I mentioned, this is part 3 of a 4-part series. In part 1, we talked about odds and probability. Then we looked at credit scores and looked at the results of credit scores versus delinquencies on a log odds scale. We looked at the formula, the function called the logistic function of P equals 1 over 1 plus e to the minus x. And we determined this might be a very useful function for us to do analysis of credit scores. And then finally, we looked at some data that was provided to us by Experian, which is anonymized credit performance data, and is the data we can use for our modeling. In part 2, we developed a simple model of a car price based on a few attributes. We used a linear regression model to do that. And then we looked at the car prices and the fit of the model using a measure called R-squared. In part 3, we're going to examine a different type of question, and this is, will I be late? So once again, we're going to do something very similar to what we did before. We're going to identify our dependent variable. We're going to create and evaluate attributes. But this time, we're going to do a logistic regression rather than a linear regression. Logistic regression might get you thinking we might be using logarithms here. Then, just like we did in the linear case, we'll assess the model and we'll make some predictions. So here's the problem. You are at the front desk or the front of a hotel, and the guests come up to you and they keep asking you, well, how much time do I going to need to get to the airport? And you've sort of studied this over time, and you have a series of outcomes based on whether or not people made it to the airport on time. In this case, we're going to say on time is whether or not you get there an hour before the flight, so you have time to check in. So we have data that we've collected over time for various trips, the time that the person left before the flight, and whether or not they were on time. And then we've graphed this data, the minutes before the flight, and the outcome. 0 means you were late, and 1 means you were on time. So looking at this, the transportation desk might say, oh, look, 120 minutes, maybe a little bit more than that. You leave more than 2 hours, you're likely to make it on time because it looks like no one has been late more than, let's say, 125 minutes. If they left 125 minutes before their flight. But maybe we can do a little bit better than this. So unlike linear regression, sometimes we want to measure binary variables. For example, did a product break? Did a borrower miss a credit card payment? Or will I be late for check-in? Right, and so the graph is going to look something like this. We have some variable, and then we have 0 if it didn't happen, 1 if it didn't happen. Well, what about linear regression? What if we just put a line through that like we did before? Looks like it's going to create some problems for us. So what are some of the problems? Well, one looked like it doesn't fit the data very well. And the question is, like, what are we trying to forecast? Like, what would it mean to be at above 1 or below 0 here? We really want to know what's the probability that will be late. So we probably want something a little bit more like the green function here that stays between 0 and 1 that we can think of as a probability. This is going to transform numbers from minus infinity to a plus infinity to a range of 0 to 1. Yes, and this looks like our logistic function we saw earlier. And we can just stick a little regression equation inside that, where y is going to be the probability and a plus bx will be the log odds. So we're going to do the same thing we did before with a linear regression. We're just going to go to Excel. We're going to put in our data. And we're going to create our regression in log odds. So this is the log odds, which is going to be our values times the variable. And then we're going to have our regression parameters, which is our intercept and our slope. We're then going to use those using these equations that we know, ones that we studied before, to convert log odds into probability, to create a probability. And then before, just like we calculated the difference between two functions, in this case, we have slightly different than we have a different error function that we're going to use based on whether or not we were right or wrong on guessing the probability. And then we're going to add that up and we're going to get a total error. And then we're going to do the same thing we did in the linear case. We're going to use Excel Solver and we're going to minimize the value of the error by changing the input values. And then we're going to get some answer, which is going to give us now the probability of being on time and the probability of being late, which is just 1 minus probability of being on time. And now, as you'd expect, as you have more minutes that you leave before your flight, your probability of being on time goes up and your probability of being late goes down. And so now you can answer the question, well, how confident do you want to be? If you only want a 50-50 chance of being on time, which is an odds of 1, log odds of 0, that's going to give you just leave 84 minutes beforehand. It's going to be somewhere right around here. If you want to have a 9% chance of being on time, 9% chance of being late, well, maybe you need 107 minutes. And if you want to get below a 1% probability, you're going to need more than 131 minutes. So here we've just transformed from just being able to look at one number to being able to look at the whole distribution and understand our probability of being late rather than just a yes/no answer. You know, before we used a graph of actual versus model to determine how well the model fit, but this is still pretty hard to judge. So just as we used R-squared, we're going to try something different for this type of model, for a logistic model. And I've shown you two different types of approaches we can use. The one on the left is we bucket the events into different categories based on the time, and then we calculate what was the probability that we were late or on time in each of those buckets. Here, I've also extended the model to add whether or not it was rush hour or not rush hour. So during rush hour, your probability of being late is much higher than during non-rush hour. And we can see that the model does a pretty good job of fitting the data. Another technique that's often used for these types of models is something called the area under the curve. And the idea of this is we look here at the percentage of cases where it didn't happen, where you weren't late, and the percentage where you were late, and say how well can, as we sort of add up all the values, produce something that goes towards this upper right-hand corner. What we want is something the further up and to the left, the better. So the bigger the area covered by these lines, the better it is. So including rush hour improves our model from not having rush hour. We'll get more into this in a later discussion of logistic modeling. So let's just quickly compare linear versus logistic models. For a linear model, we use the function alpha plus beta x plus epsilon or error. And for a logistic model, we're going to use this function where we put the log odds into here, do the regression in this portion of the model, and then we can convert it into a probability. So in a linear regression, our dependent variable is a number. In a logistic variable, our dependent variable is binary, 0 or 1. We can have any sorts of independent variables, either real or categorical. The real difference comes in the output of the model. Linear regression is going to give us an estimated value, and a logistic model is going to give us a probability of an event, not the actual event or not a price, but a probability. I said we have two different equations for these models, and then we're going to use our regression method is either the sum of the squared errors, or here the sum of the log losses with the loss function. And for performance, while we used R squared for linear regression, we're going to use an area under the curve or other similar measure for a logistic regression. With that background in mind, we're going to be ready for part 4, which is how we actually turn a credit data into a credit score. And I hope you'll join us for part 4. Thank you for your attention. Once again, if you would like some more information about PhiCycle, please click on the QR code here, and we look forward to talking to you in the future. Thank you.